Welcome students to the next lecture of digital communication. So in the last video lecture we were discussing about the concepts of information theory, and we were trying to understand the the fundamentals behind how to quantify the amount of information contained in a message in terms of its probability. And we also defined a few terms like the entropy, and how entropy is described as the average information um, for a message. And then we discussed about mutual information, and we talked about how in a noisy channel the entropy is reduced because of the channel noise disturbances, or in other words how the effect of noise generates a kind of negative information, and that reduces the overall information that is emitted from the source, and so on. And we solved some example problems also. So in today's lecture we will revisit our discussion about the discrete memoryless channel. So during the start of the semester we talked about the discrete memoryless channel, and here you can see the diagram that denotes a discrete memoryless channel. So we have an alphabet source X, and you can have different source symbols as a part of that alphabet, x1 x2 up to xm, and then you have an output alphabet Y, and different symbols y1 y2 etc. as a part of that alphabet. So there was a source, and then there is a destination, or let's say a receiver, where you have this output alphabet. And then these transition probabilities, which are different conditional probabilities, they define the discrete memoryless channel. So whatever is in between, is between the source and the destination, is your discrete memoryless channel. And the channel is actually characterized by this transition probability. Okay, so so we will revisit the concepts of the discrete memoryless channel. So earlier we we tried to find out the probability of error at the receiver from this channel transition probabilities. So now we will use these very probabilities, these transition probabilities, to find out the information that is emitted by the source, and the information that is received, and whatever is the information that is lost because of the channel noises. And then we will try to define from the concepts of information theory a new concept called the capacity. Okay, so this is not so new. Okay, you have also come across this concept of capacity from your prior learning in this semester. So you have known that the Shannon channel capacity is defined as C equal to the bandwidth times log to the base 2 of 1 plus signal to noise ratio. So so this formula actually is derived based on the assumption that your channel is additive white Gaussian noise channel. And this definition of the capacity actually comes from the information theoretic point of view of the channel. So we will define capacity in this lecture, and we will first learn that what exactly is the capacity of a channel given a channel like this, like the discrete memoryless channel that we are seeing here. We will define from the fundamentals of information theory, and um, also mathematically we will define what is capacity C of a channel. And then later on in some future lecture you will also see that if you apply the concepts or the mathematical definition of capacity, then you will get this value, assuming that the channel is AWGN. But this part is reserved for a later lecture. But in this lecture we will first define what is capacity, okay, from the information theoretic point of view. So so let us first do an analysis of the discrete memoryless channel from the perspective of information theory, okay. So we will use some of the given knowledge about the discrete memoryless channel. So by given knowledge I mean that we know that we have these transition probabilities and we have this a priori probabilities, right? So these were called the a priori probabilities, which you have learned before. So these were known, and also these are the channel transition probabilities that defines the discrete memoryless channel. So these are also known, okay. So these transition probabilities are also known, and and then given these quantities, okay, so these probabilities are given, so these define the discrete memoryless channel, okay. So so you can calculate the joint probabilities x, j, y, k by using Bayes rule from the given parameters of the discrete memoryless channel, which are the transition probabilities and the a priori probabilities, okay. And then the probability of yk being output by the channel can be calculated by summing over all j of these joint probabilities, okay. So if you sum over one particular variable of a joint distribution, then you get the marginal distribution of another variable. So that's what we are trying to obtain by summing over all j's equal to 1 to m. And this joint probability, as we have seen here, is this expression, right? So so from this, once we calculate the probabilities of yks, then we can calculate the a posteriori probabilities also, okay. So the a posteriori probability are defined as the probability that xj was the input given that you observe yk at the output. So this conditional probability can be written like this, okay. This is again from the fundamentals of probability theory. So now you know these joint probabilities from this expression, okay. So these are all given, okay. They are the parameters of the discrete memoryless channel. So you can calculate the joint probability, and then you can also calculate the probability of yk using whatever information is given. And therefore now, using the concepts of information theory that you have learned so far, and so we can calculate the uncertainty about the input symbol after we have received yk. So we are observing yks at the output, and we can calculate these probabilities, that what is the probability that xj was at the input given that we observed yk. And once we can calculate these, we can also calculate the entropy or the uncertainty about the input symbol. Okay, so you can calculate the entropy of the entire input capital X given you observe yk, and that can be written from the definition of the entropy that you learned so far. So this is basically the average over all these a posteriori probability distribution. Okay, so you calculate the a posteriori probabilities, and then this part gives you the information from the definition of information that you learned in the previous class. So this is minus logarithm to the base 2 of these a posteriori probabilities. So that gives you the information that you obtain about xj's given you observe yk. Okay, so now if you just use this weighted sum by multiplying the same probabilities in front, you get the average information about the input xj's given given you observe yk, and then this is the sum over all j's. So in that way, this is the average information of all the inputs x given you observe any output yk. Okay, and that from the definition of the term itself is the entropy of the input alphabet capital X given you observe yk. Okay, so now if you do the average over all k's now, okay, so this is for this term that we obtain the expression for is for one particular observation of the output yk. Okay, now if you average the entire thing by multiplying with the probabilities of yk and summing over all k's, then you get the conditional entropy of the entire input alphabet x given the output alphabet y is observed. So so this is basically going back to the few slides back here. So if you observe all these output symbols that are part of this entire output alphabet, and then based on that observation you are trying to find out what is the information that is contained in the input alphabet x which contains all these symbols. Okay, so that term is given by this h of x given y. Okay, so in the previous video lecture we came across this term conditional entropy, h of x given y, but at that case we were considering two sources x and y. Okay, which were trying to you know trying to source information together. Okay, so that was the notion there. Both of these x and y was an input that was giving out information together, and we were trying to study that if x and y are somewhat related, then what would be the information that we obtain from x given we observe y. In this case, this h of xy is meant for, again, two random entities, but in this case instead of both being the source randomly emitting some information, in this case what we are studying in this particular video lecture. In this case, we are considering x and y as the source and the destination. Okay, and we are randomly observing the destination, whatever is the output here, and then trying to find out some information about the input x. Okay, so from the concept of information theory, or from the probabilistic point of view, um, we are basically doing the same thing what we did in the previous lecture and what we are doing here. Basically, we are trying to observe a system which has two random entities, x and y. Okay, and the information that both of them are generating has some relation. So the information that x is generating is obviously related to what you are observing at y, because the same information is traveling through the channel and then you are observing at y. So x and y are two random entities, but they are somewhat dependent. Okay, and and you are trying to find out the information that is emitted by one of the random entities by observing the other random entity. Okay, so just to draw a similarity between the two situations, this was the previous lecture where two random entities were considered as the source, and then if they are emitting information together, and if they are some way related or dependent, then what is the effect on the mutual information and entropy of the system? If they are not related, then what is the scenario? We were doing that. Here we have defined x and y as the input and the output of the discrete memoryless channel, and we are trying to find out the relationship between these two, or in other words, we are trying to find out the information that is given by x based on our observation of y. Okay, so we are defining h of x given y based on this model here, but mathematically nothing changes. Mathematically the definition remains the same, and we have h of x given y is basically the probabilities, I mean the information of those xj given yk. Okay, the information obtained from these probabilities, and then they are weighted over the joint probabilities and then summed over all j and k. Okay, so this conditional entropy, okay, is also called the equivocation. So again, you learned about this term equivocation in the previous video lecture, and both have the same meaning. In the previous in the previous lecture, you saw that equivocation meant the amount of information that was getting lost because of the noisy channel. Okay, here also it means the same. Okay, so let's say your x is the source, okay, as per the model that we are assuming for this lecture. So whatever entropy or information that is emitted from the source and whatever is getting lost because of the channel. Okay, so when you are observing y, you are actually observing it after the channel has affected the information. Okay, and based on that observation you are trying to find out what was x. Okay, so these actually is giving you the equivocation, or the amount of information that is lost in the channel. Okay, so that part is subtracted from the original entropy of the source, and that finally gives you the mutual information between x and y. Okay, so so x is emitting some information and you are observing y and trying to find out that information. So that mutual information between x and y is basically whatever information that x is originally emitting, which is represented by this entropy of x, minus the um, the conditional entropy, which is also called the equivocation, and this is the uncertainty which is lost in the channel. Okay, so so having said that, now that we have defined the mutual information between the source and the destination, okay, so from now on this x means your source and y means your destination. Okay, so the mutual information between x and y is the term that is of our interest now. Okay, so now we can define channel capacity. Okay, so remember that you have learned about capacity before in your wireless communication and digital communication classes. You also have come across the Shannon channel capacity formula, the Nyquist channel capacity. So that channel capacity actually can be also defined in terms of the mutual information. Okay, so let's look into the definition of the capacity for a discrete memoryless channel. So the capacity of the discrete memoryless channel is the maximum information transfer per symbol. Okay, so basically in mathematical terms, whatever I of x, y of the mutual information that you have, which is given by the entropy of the source minus the equivocation term. Okay, so this quantity, whatever it is, if you maximize this quantity over all the input probabilities, okay, then you get the channel capacities. Okay, so this is important and interesting also. So basically this term I x y of the mutual information is basically a function of all the probabilities. Okay, so I x y is basically hx minus h of x given y, and hx and h of x given y, these are entropies, and at the end of the day these entropies are nothing but the functions of the probabilities, because the definition of information can be written in terms of the log of the probabilities, and then the entropy is nothing but the average information. So at the end of the day, this hx and hx given y, these terms can be expressed as the probabilities. Okay, and those probabilities, whatever probabilities that are associated with the discrete memoryless channel, you have seen from this slide that all the probabilities, probability of xj comma yk, I mean the the joint probabilities, the a posteriori probabilities, everything can be expressed as this. Okay, so this pyk can be written in terms of pxj and p of yk given xj. Okay, and then the entropy can be written in terms of pxj's also. Okay, so so at the end of the day, these term, this ix semicolon y of the mutual information between x and y, okay, these term is actually a function of the input probabilities. Okay, this term is a function of basically the input probabilities and the and the transition probabilities. Okay, so so if you want to maximize this term, you have to maximize it over all the input probabilities p of xj's. Okay, so you can just twist and turn these values, okay, so that whichever gives you the maximum ixy. Okay, so so based on all these probabilities p of xj, okay, let me write p of x1, okay, um, p of x2, etc. So these are all the p of xj's. Okay, these are all the p of xj's. Okay, and they can be written like p of x1 x2 up to p of xm, because there are m symbols in the input alphabet. Okay, so based on their values, whatever value they take, okay, you can calculate different I x y. Okay, let's say this is half, this is 1/3, whatever, and let's say this is 1/4. Okay, and in between also there are many values. Okay, and then you get an ixy for this. Let's say this is a 1/4, this is half, and so on. You get another ixy for this. So whatever values of the input probabilities maximizes the ixy. Okay, so you look up all the values of ixy based on whatever values the input probabilities can take, and then you can you can find out which values of the input probabilities gives the maximum value of ixy, and that maximum value is actually the channel capacity. Okay, but there has to be a certain constraint. So these values has to be always non-zero. Okay, so that is one constraint, subject to the constraints that p of xj should be greater than equal to 0. So this can be 0 or greater than 0. Okay, which is very obvious because that's directly from the definition of the probabilities. They can be only greater than or equal to 0. So this constraint has to be imposed. You cannot put a negative value here, okay, as the probability and then maximize this term. This has to be greater than or equal to 0, and also this constraint has to be imposed as well, that the sum of all the input probabilities will give you 1. Okay, so whenever you choose the value of pxj's to maximize this quantity I of x semicolon y, or the mutual information, you have to ensure that they are either 0 or higher and the total sum is equal to 1. And then keeping these two constraints, you can just choose any value and you can just play with the value of the probabilities until and unless you get the maximum value of ixy. And that maximum value of ixy, whatever you get, is your channel capacity. Okay, so this is the information theoretic definition of channel capacity. Okay, so let's look into an example. So let's consider the binary symmetric channel that you studied so far. Okay, so the binary symmetric channel had two inputs x1 and x2 and two output y1 and y2, right? And let's say the probability of x1 is alpha and probability of x2 is 1 minus alpha. So these are the input probabilities that we were talking about in the previous slide. Okay, and and let's say the channel transition probabilities are given as what is the probability that you will get y2 given you transmitted x1. Let's say that is p, and then this is 1 minus p. Okay, and again this probability is p and this is 1 minus p. Okay, So so these are the transition probabilities. Okay, so now we have to find out the channel capacity, okay, which is by definition the maximum of I of x semicolon y, or the mutual information between x and y over all the input probabilities. And the input probabilities are basically given in terms of alpha. Okay, one of them is alpha, the other one is 1 minus alpha. So here you note that already the constraint that the sum of all the input probabilities um, over all j, this is equal to 1, okay, as per the condition in the previous slide, as per this condition. Okay, so so this is already 1 because here you have chosen them as alpha and 1 minus alpha. So alpha plus 1 minus alpha is equal to 1. Okay, so this is your p of x1 plus p of x2. So these are this, in this case your j is 2, you have two inputs, and then p is the crossover probability, and you define the channel transition probabilities in terms of p and 1 minus p. So when you are trying to find out c, which is the maximum of I x y, the maximized over all the input probabilities, you are basically maximizing I x y over all the alpha, because the input probabilities are given in terms of alpha. Okay, so I x y again from definition is this h y minus h of y given x, and by the definition of conditional entropy you have h of y given x as this. Okay, so we will calculate based on the transition probabilities and the joint probabilities what is the value of h of y given x. So h of y given x is basically calculated like this. So you know all the transition probabilities from here. Okay, so these are all the transition probabilities which are either p or 1 minus p, and the input, I mean the joint probability can be calculated. Let's say p of xj comma yk can be calculated as p of xj times p of yk given xj, right? So these yk given xj's are these probabilities, either they are p or 1 minus p, and p of xj is either alpha or 1 minus alpha. If it is x1 then it is alpha, if it is x2 then 1 minus alpha. So you can put all these values here. So see, the final expression is in terms of either alpha, okay, or p. Okay, and then if you simplify this you will get an expression which is all based on p, because the alpha terms just cancel out. Okay, if you just check into this expression and say try to simplify it yourself, you will see that the alpha terms just cancels out, and you have only left with this term. Okay, so therefore, so this is the h of y given x. Okay, so my I of xy is basically h of y minus this term. So that means my I of xy is h of y plus whatever we get here, p log 2p and 1 minus p log 2 1 minus p. So this is basically independent of alpha. Okay, we were supposed to maximize this expression over all alpha, but this expression is totally missing alpha. Okay, so now that we just got rid of all the alpha, just see, let us see what will be the maximum value of this expression anyway. So this expression will be at a maximum when hy is maximized. Okay, so this is fixed. Okay, this p is the crossover probability. So this is the property of the channel and this is fixed. Okay, so this part is fixed. So only this expression is maximized only when this hy is maximized. Okay, and we know that the maximum hy, which is 1 bit per symbol, is occurring when your two output symbols py1 and py2, they are equiprobable. Okay, so you remember we did a graph like this of h of x. Okay, so this was maximum when probability of x1 equal to probability of x2. From your previous lecture you can recall this. So similarly here also we are dealing with h of y, and this will be maximum based on the same concept. This will be maximum when p of y1 and p of y2 are equal and equal to half. Okay, so so p of y1 and p of y2 is equal to half when p of x1 and p of x2 is also half. Okay, so basically you can see here what is meant by having the probability of y1 and probability of y2 equal to half. So this is the discrete memoryless channel, or the binary symmetric channel that we were discussing in that example. So if you see that if the input probabilities are alpha and 1 minus alpha, and the transition probabilities as 1 minus p and p, then if you calculate py1 and py2 according to these expressions, okay, then you end up having this expression for py1, and for py2 you have this expression. Okay, so so if you want to have py1 equal to py2, okay, and that 2 equal to half, so if you want to have this equal to half, you can observe that that means basically let's say alpha, okay, if you choose alpha equal to half and p equal to half in these expressions, then what you have is basically this is alpha plus p, so half plus half is 1 minus let me do it, this is half plus half minus twice of half into half. Okay, so this will give you half. Okay, so this will be equal to half, and this will also be equal to half, and these two will be equal. So if you choose alpha equal to half and p equal to half, so that means if you choose alpha equal to half, then that means that p of x1 is also equal to p of x2 equal to half, because alpha equal to half and 1 minus alpha is also half. So p of x1 and p of x2 is also equal to half. So that means to maximize the capacity, okay, or sorry, to maximize the mutual information, you have to maximize h of y, and h of y is maximized when your p of y1 is equal to p of y2 equal to half from the analysis that we did before, because entropy gives entropy of any number or any quantity is maximum when the input probabilities are equal or equiprobable. Okay, so from that perspective we deduce that h of y will be maximum when p of y1 and p of y2 is equal to half, And we just saw that for the binary symmetric channel, if you want to have P of y1 and P of y2 equal to half, then P of x1 and P of x2 will also be equal to half. Okay. So with this, the final expression of capacity, which is the maximum of I of x, y, maximized over all the input probabilities, is basically this expression. So this is 1 plus, so 1 is the maximum value of this hy. Okay, so in this expression, if we just replace the maximum value of hy, which is 1, then we get the maximum value of ixy. Okay, and that maximum value is the value of your capacity. Okay, so if you plot the capacity that you obtain, so C is basically, your C is basically, let me erase this, so your C is basically 1 plus P log 2P plus 1 minus P log 2P. Okay, so if you just plot your C, okay, so this is your, this relative channel capacity is this y-axis, and this P is the bit error rate, okay, or the flipping probability. So if you plot P versus capacity, then when your P is half, your channel capacity is minimum, okay, but when your P is equal to 0, you have the maximum value of the channel capacity, which is 1. So let me look back again. When your P is 0, okay, then both of these terms are 0, okay, and you are left with 1. Okay, so P, when P equal to 0, you have 1. When P equal to half, you can see that this will give you 0. Okay, and when P equal to 1, then also this expression will be 1. Okay, so so you can see that when your P is half, you have the capacity as 0. When P equal to 0, you have 1, and when P equal to 1 also, you have the capacity as 1. So let's analyze this. So when P equal to 0, the capacity is maximum. This makes sense since the channel is error free in this case. So if you recall the discrete memoryless channel, or the binary symmetric channel, so this crossover probability is P. Okay, so you are transmitting x1 and you are getting y2. Okay, similarly when you are transmitting x2 and getting y1, the crossover probability is P. So basically P0 means you're transmitting x1 and you are getting y1. There is no chance of flip over of this bit. Okay, when your x1 is let's say your x1 is 0 and x2 is 1. Okay, and y1 is 0 and y2 is 1. Okay, so when you are transmitting a 0, you are also obtaining a 0 without any error, and when you are transmitting a 0 and obtaining a 1, so this is the actually probability of making an error. Okay, so your P equal to 0 means that your channel is error free. Okay, so this makes sense because when your channel is error free, your capacity is maximum. Okay, again when your P equal to half, then the capacity is 0, because in that case the channel is useless. Okay, so when your flip over probability is half, then this 1 minus P is also half. Okay, so basically when you are transmitting a 0, then with 50% chance you can receive a 0, or with another 50% chance you can receive a 1. So this makes your channel useless because it is as good as just tossing a coin and predicting the output based on whether it is head or tail. Okay, So your channel is of no value. So in that case, your capacity is 0. So therefore, this makes sense. Again, when p equal to 1, so then the channel behaves as a complement channel. Okay. So when your p is 1, it means that when you are sending a 0, with 100% probability that will be flipped to 1. Okay, when you are sending a 1, with 100% probability that will be flipped to 0. So that means your channel behaves as a complement channel, or rather you are implementing a bit complement operation at the receiver. Okay, so you can still recover your data. Okay, so these two scenarios, when p equal to 1 and p equal to 0, are basically equivalent, and at that two scenarios you are getting the capacity equal to 1, the maximum values. For any other value of p, the capacity decreases, and the minimum possible capacity, which is 0, occurs at p equal to half or 0.5. Okay, so this is an interesting result that we just obtained. Okay, so now let us move on. We will do more examples of calculating the capacities later. So right now, just stick to the mathematical definition that we discussed so far, which is capacity is equal to the maximum of the mutual information maximized over all the input probabilities, subject to the constraint that the sum of all the input probabilities will be equal to 1, and in each individual probabilities will be greater than equal to 0. Okay, so this is the definition of the capacity. Later on we will see in some tutorial later that if you assume additive wide Gaussian noise channel, then um, then the capacity that is obtained from this definition gives you the famous Shannon channel capacity formula. Okay, we will do it in a later class. Okay, or in some tutorial class later. So we are moving on with the next concept, which is called source coding. So source coding does not change or alter the source entropy. Okay, the average number of information bits per source symbol is not changed also. Source coding does alter the entropy of the source coded symbols. Okay, it may also reduce fluctuations in the information rate from the source and avoid symbol surges, which could overload the channel when the message sequence contains many high probability symbols. Okay, so let's see. So so we can define code efficiency by the actual entropy of the source divided by the maximum entropy times 100%. Okay, so if the source symbols are coded into another symbol set, then the new code efficiency will be computed by the above formula, where H is the entropy and H max is the maximum possible entropy of the new symbol set. Okay, so for a set of symbols represented by binary code words with length LM digits, a code length L can be defined as the average code word length. Okay, so this capital L is basically the weighted sum of all the LMs weighted by the probability of the messages PM. Okay, so then code efficiency will be H over L times 100%. Okay, so basically your H max is equal to the capital L. So let's do an example. Okay, so let's say a scanner converts a black and white document line by line into binary data for transmission. The scanner produces source data comprising symbols representing runs of up to 6 similar image pixel elements with the probabilities as shown below. Okay, so you have this data, so number of consecutive pixels and their probabilities of occurrence. Okay, so one pixel is very frequent to occur with 0.2 probability. 2 pixels is basically the maximum occurrence with the highest probability, 0.4. um, like 5 pixels is very less occurring with 0.06 probability. So you have to determine the average length of a run in pixels and the corresponding effective information rate for the source when scanner is traversing at 1000 pixels per second. Okay, so let's see. So you have all these probabilities that are given, and from that you can calculate the entropy, which is equal to 2.29 bits per symbol, and the average length can be calculated by this formula. So your LM is given, that was like 1, 2, 3, 4, 5, and 6 with their consecutive probabilities. So you can calculate the average length as 2.69 pixels. Okay, so at 1000 pixels per second scan rate, we can generate about 1000 divided by 2.69, 372 symbols per second. So therefore the source information rate is 2.29 times 372, 852 bits per second. So we are generally interested in finding more efficient codes which represent the same information using fewer digits on the average. Okay. So this results in using different lengths of code words for different symbols. The problem with such variable length code is in recognizing the start and end of the symbols. Okay. So that is a problem, and therefore while decoding the variable length code words, the following properties need to be considered when attempting to decode. Okay, so that is unique decoding and instantaneous decoding. Okay, so unique decoding, this is essentially if the received message is to have only a single positive meaning. So let's consider M equal to 4 symbol alphabet with symbols represented by binary digits. Okay, so A is represented by 0, B is represented by 0, 1, C equals to 1, 1, and D equals to 0, 0. So if we receive the code word 0, 0, 1, 1, it is not known whether the transmission was D, C, or A, C. Okay, so 0, 0, 1, 1 can be D and C, or A, C, because if you receive A, that is 0, another A is 0, and then 1, 1 is C. Okay, so this example is not uniquely decodable. Okay, but if we have this type of binary representation, let's say A equal to 0, B equal to 1, 0, C equal to 1, 1, 0, and D equal to 1, 1, 1. So this code can be instantaneously decoded using this decision tree. So if let's say you are at an initial state here, and if you have a 0, okay, so that can be A, okay, that can be decoded as A. If you have a 1, okay, so that 1 can be due to B, C, or D, because all of them has a 1 at the beginning. So you wait for the next state and see that if the next state is 0, so that means if the next state is 0, so you have 1, 0, and that corresponds to B. But if you have a 1 again, so you see that you have a 1, 1, okay, and 1, 1 can be either C or D. So you wait for the next state and see if it is a 0. If it is a 0, then it's 1, 1, 0, So that means it's C. If it is a 1, then it's a 1 1 1. That means it's a D. Okay. So in this code, no complete code word is a prefix of a larger code word. Okay. So so 1 0 is not a prefix of any of these. 0 is not a prefix of the other 3, and so on. So in the previous case, this 0 is a prefix of B, because B contains 0 1. Okay. This 0 is also a prefix of D. Okay. So this is basically a situation which is not very useful. In this case, you can see that no complete code word is a prefix of a larger code word, and therefore you can uniquely decode that using this decision tree. Okay. So this type of code is also called a comma code, as symbol 0 indicates the end of a code word, except for all ones word whose length is known. Okay. So 0 means the end of a code word. This is A equal to 0, B equal to 1 0 end, C equal to 1 1 0 end, except for the all one case, and for that you know the length of the code word. So this is a way of assigning code words, so that you can have variable length code words, and at the same time you can uniquely decode them by looking at the code words. Okay. So let's see an example again. So assume a name equal to 8 symbol source emitting this letters A to H and having the probabilities of symbol occurrence given by all these values. Okay. So the source entropy is simply given by this definition of entropy, which calculates to 2.55 bits per symbol. And the maximum entropy H max that you can have for 8 symbol source is basically log of 8 to the base 2, which is 3. So therefore the source efficiency is 2.55 over 3 times 100%, so that is 85%. Now you can use variable length codes, okay, to increase the efficiency. Okay. So if the symbols are each allocated 3 bits comprising all the binary patterns between 0 0 0 and 1 1 1, the coding efficiency will remain unchanged. Okay. But Shannon-Fano coding, which is a type of coding in which we allocate the regularly used messages fewer bits, is more efficient. Okay. So the highly probable messages will get fewer bits, and the less probable messages will get higher bits. So in that way you can design a variable length code, and this will yield in the improvement in efficiency compared with that before source coding. Okay. So so you can decode this type of variable length codes using the Huffman coding algorithm. Okay. So the Huffman coding algorithm has 2 steps: reduction and splitting. Okay. So we will just go through this reduction and splitting with an example. So let's say in the previous example, this particular example, we have all these letters with their probabilities. We just arrange them in the order of highest to lowest. So C has the highest probability and H has the lowest probability. In any case, you saw from this particular slide that if you assign fewer bits to the highly probable messages and more number of bits to the less probable messages, then you can design an efficient variable length code which has higher efficiency. Okay, so we will see how. So first let us assign the code to these letters based on their probabilities, but before that we have actually sorted these letters according to their probability of occurrence, and we will see using the Huffman coding algorithm how to assign the code words. Okay, so after we have sorted them from highest to lowest, um, we will do these things. We will take the lowest two, okay, and we will take the sum, okay. So 0.05 and 0.04 gives you 0.09, and this goes here and in between these numbers. So 0.10 is for F, okay, and for G and E we have 0.07 and 0.06. If we add this, we get 0.09. So 0.09 should come between 0.10 and 0.07. Okay. So then again we sum these two numbers. Okay, and then this goes here between 0.18 and 0.10. Okay. Again we take the last two and sum them, and that gives you 0.19. So that comes between 0.4 and 0.18. And you keep doing this, and your your entire, um, this probability arrangements are getting reduced. Okay, so this is what is reduction. Okay, so you are basically reducing this unless you get a 1. Okay, so now that you have done the reduction part, now you have to do the splitting. Okay, so in the splitting you just look from behind, you look from this particular direction. Okay, so you look from here and then you assign a 0 and 1 to the previously occurring branches. Okay, so you assign a 0 and 1, then this 1 is propagated here because this 0.40 is coming from this step. So this 1 is propagated here. This 0, which is equivalent to this 0.60, that comes from the sum of these two, 0.37 and 0.23 in the previous stage. So you put another 0 to the left here, so then you get 0, 0 and 0, 1. Okay, now you propagate like this. So this 0, 1, I mean this 0.23 comes from this 0.23, so this 0, 1 is here now. Okay, and this 0, 0, which is corresponding to this 0.37, this 0, 0 is propagated this way with another 0 here on the, another 0 here and another 1 here. Okay, and this 0.37 comes from 0.19 and 0.18. So this 0, 0 comes here with another 0 added here and another 1 added here. Okay, so we will follow this same pattern. Okay, so we will have this 0, 0, 0 goes here, and this 0, 0, 1 goes here. Okay, but this 0, 1 becomes 0, 1, 0 and 0, 1, 1. Okay, and then again this 0, 0, 1 goes here, this 0, 1, 0 goes here, this 0, 1, 1 goes here, but this 0, 0, 0 goes to the previous stage as a split between these two probabilities. So this becomes 0, 0, 0 with another 0 and another 1. So 0, 0, 0, 0 and 0, 0, 0, 1. And then you propagate again, and this 0, 1, 1 goes here, this 0, 0, 0, 0 goes here, this 0, 0, 0, 1 goes here, but this 0, 1, 0 goes in this stage and it gets split to 0, 1, 0, 0 and 0, 1, 0, 1. Okay, and then finally this 0, 1, 0, 0 goes here, this 0, 1, 0, 1 goes here, and then this 0, 0, 0, 1 becomes split to 0, 0, 0, 1, 0 and 0, 0, 0, 1, 1. Okay, and the remaining values are propagated as as it is. Okay, so this one gets propagated until all the stages, and then this 001 gets propagated. Okay, this 011 gets propagated, this 4 zeros gets propagated like this. So this is how you do the splitting, and then finally when the algorithm ends you are left with the corresponding code words in red that each of these symbols should have. Okay, and you can see that the highest probability code word gets the lowest length, and the lowest probability code words gets the highest length. Okay, so in that way you design the code words using the Huffman coding algorithm. Okay, and once you get the code words, the code length, the average code length L is 2.61, and you can see you can increase the coding efficiency to 97.7%. Earlier it was 2.55 over 3, and it was actually 85%. So by designing a variable length code using the Huffman coding algorithm, you get the average code length equal to 2.61, and in that way you can get 97.7% coding efficiency. So with this I will stop here, and I will see you in the next video lecture. Thank you.